everyone, welcome back to the deep dive. You know the drill, right? We go deep, we go fast, we get to the heart of complex stuff, stuff that really matters. And today, oh boy, today we are diving into the world of AI, and specifically we're going to untangle three concepts that everyone kind of throws around, but not everyone fully gets. We're talking about reinforcement learning, supervised learning, and of course, deep learning.
Yeah, I mean, these are the building blocks, really. You see them everywhere in AI. Like when your email filters out spam, that's AI at work, right? Or think about self-driving cars or, those AIs that can beat grandmasters at chess or Go. All of those rely on these fundamental concepts. And like you said, it's easy to get them mixed up or not quite grasp the nuances. But trust me, understanding the differences, especially like how reinforcement learning compares to deep learning and supervised learning, it's crucial. Like it gives you a real edge in understanding just how powerful AI is becoming.
Totally. And the thing is, you don't have to be an engineer or a data scientist to benefit from this knowledge. Knowing how these mechanisms work, it's like having an X-ray vision into the AI systems we use every single day. Plus, we're going to delve into deep reinforcement learning as well, which is where things get really interesting.
Oh, absolutely. Deep reinforcement learning is where these concepts really converge and, unlock some pretty amazing capabilities.
Yeah.
And to make sure we're giving you the best possible view, we've been digging into a bunch of articles that lay out these AI paradigms in a way that will frankly just make sense.
Right on. So no jargon overload here. Our mission is to equip you, the listener, with a solid grasp of these machine learning methodologies and why they're so important in the current AI landscape. So yeah, let's unpack this whole thing, starting with, I guess, the most fundamental concept, at least in my mind, supervised learning. What's the basic idea behind it?
So imagine you're trying to learn. Let's say you're trying to learn about different types of birds, right? You have a teacher, and that teacher shows you a robin and says, this is a robin. And it shows you a sparrow, this is a sparrow, and so on. Supervised learning is kind of like that. You have these labeled examples, and each input, like an image of a bird in our case, has a corresponding correct output, which is the label robin, sparrow, and so on.
Got it. So the AI learns from these examples where the answer is already given.
Exactly. The AI model tries to predict the output, and then it checks its prediction against the actual label. Based on how far off it was, it makes small adjustments to improve its future predictions. It's all about refining its performance based on the feedback it gets from those labels.
Makes sense. So are there specific types of problems that supervised learning is good at solving?
Oh, definitely. One is classification, which is basically sorting things into categories. Like, imagine an AI that can identify different plant species based on pictures of their leaves. Each picture would be labeled with the correct species, and the AI would learn to do that sorting itself.
Right, so sorting emails into spam or not spam, that kind of thing.
Exactly. And the other big one is regression, which is about predicting numerical values. Think about, say, predicting the price of a used car. You'd feed the AI data about the car's mileage, age, features, and, the actual selling prices from the past. And the AI would then try to predict the price of a new used car based on those factors.
So in both cases, it's about having a history of known answers, right? Someone somewhere had to label those images or record those car prices.
Absolutely. The key here is having enough of that labeled data. The more examples you have, the better the AI can learn. And of course, the quality of that data is crucial too. If your labels are wrong, your AI is going to learn the wrong things.
Makes sense. Can you give a couple more examples of where supervised learning is being used right now, stuff we're interacting with on a daily basis?
Oh, tons. Think about medical image analysis, where AI is being used to detect tumors or other abnormalities in scans, or in financial fraud detection, where AI can analyze transactions in real time to flag suspicious activity. And then there are things like spam filters, recommendation systems, you name it. Supervised learning is pretty much everywhere in AI. And the algorithms themselves, they're quite diverse. We have support vector machines, random forests, and of course neural networks trained on labeled data. And yeah, it really forms the foundation of many AI applications we use every day.
Okay, so we've got supervised learning where you get those explicit corrections, the right and wrong answers. How does that contrast with reinforcement learning where the learning process is, it's quite different, isn't it?
Yeah, the core difference, and we'll dive deeper into this in a bit, is that reinforcement learning doesn't have those direct answers. Instead, it's more like learning from experience. The AI interacts with an environment and receives feedback based on its actions. That feedback could be a reward for doing something good or the penalty for doing something bad. But it's not explicitly told what the correct action is. It has to figure that out itself.
Got it. Okay, before we jump into reinforcement learning, though, there's another big one we got to tackle. Deep learning. Like, what makes the learning deep in this case?
So imagine you have a simple neural network. It's like a single layer of interconnected nodes that process information. That's kind of like a shallow network. But when you start adding more layers, more of those interconnected nodes stacked on top of each other, that's when you get deep learning. Each layer learns to extract different features from the data, and as you add more layers, the network can learn increasingly complex and abstract representations of the input.
So it's like breaking down information into multiple levels of detail, right? Like going from simple edges to shapes to, I don't know, recognizing an entire object.
Exactly. And the beauty of deep learning is that it doesn't need us to tell it which features to look for. It figures that out on its own by analyzing tons and tons of data. So in our bird example, instead of us saying, look for the beak shape or the wingspan, the deep learning algorithm would learn to recognize those features by itself, just by seeing lots of examples of birds. And sometimes it even finds patterns that we humans would never even think of.
That's pretty amazing. So how does a deep learning model actually learn? Like, what's happening inside those layers?
So each of those interconnected nodes or neurons has a set of weights associated with it. These weights determine how much influence the incoming signals have on that neuron's output. During training, the network adjusts these weights based on the errors it makes.
Yep.
It's like fine-tuning the connections to get better and better at its task. It's kind of like adjusting the knobs on an old radio to get the clearest signal.
So where does deep learning really shine? Like, what kind of problems is it best suited for?
It's become the go-to approach for dealing with unstructured data. Things like images, audio, text, where the information isn't neatly organized into rows and columns. Deep learning has revolutionized fields like computer vision, natural language processing, and speech recognition.
Can you give us some specific examples of deep learning in action, like those really cool AI models we hear about all the time?
Sure. Convolutional neural networks, or CNNs, are the workhorse behind a lot of image analysis, things like object recognition, facial recognition, even image generation. And then there are transformer networks, which are behind models like ChatGPT, the ones that can generate human-like text.
Right, right. So these incredibly sophisticated AI systems, they're often built on top of these deep learning architectures.
Exactly. But it's important to remember that deep learning, it's a bit of a hungry beast. It needs huge amounts of data to train properly, and it requires serious computing power, often involving specialized hardware like GPUs or even TPUs.
Okay, so that's where the costs come in, right? Like all that training data and processing power.
Right. But the potential payoff is huge, too. We're talking about AI systems that can outperform humans in specific tasks, things like image classification or playing certain games. And, that's just the beginning, really. There's so much more to come.
Now, here's where things get a bit murky for a lot of people. We hear deep learning and reinforcement learning used almost interchangeably sometimes. Are they really the same thing?
No, not at all. And that's a super important distinction to make. Deep learning is really a set of techniques or tools, specifically those deep neural networks, that can be used in various learning paradigms. It's not a learning paradigm itself in the same way that supervised learning or reinforcement learning are. In fact, many deep learning applications fall under supervised learning, where those deep networks are trained on labeled data.
Okay, so deep learning is the tool, and the learning paradigms like supervised learning or reinforcement learning, they're the strategies, right?
Precisely. And the reason they get confused is that deep learning refers to the architecture of the model, whereas reinforcement learning describes the learning process itself. They operate on different levels, you see.
Okay, I'm starting to see the light here. So deep learning is those multi-layered networks. Supervised learning is the how, learning from labeled examples. Now, let's unpack reinforcement learning. What's the core idea there?
It's kind of like, think about how humans and animals learn, We try things, we see what happens. If we do something good, we get a reward. If we mess up, we might get punished, or at least not get the outcome we wanted. Reinforcement learning formalizes that idea. You have an agent, which could be a piece of software, a robot, you name it, and it interacts with an environment. And based on its actions, it receives rewards or penalties. Its goal is to figure out the best actions to take to get the most rewards over time.
So it's like learning through trial and error, figuring out what works and what doesn't.
Exactly. And the agent doesn't need someone to tell it the right answer every time. It learns from the consequences of its actions. Like, think about a kid learning to ride a bike. They wobble, they fall, but eventually they figure out how to balance and pedal, and they get the reward of, actually riding the bike.
Right. So there's no teacher in reinforcement learning, just a system of rewards and penalties?
Right. The agent has to explore its environment, try different things, and learn from the feedback it gets. And that feedback isn't always immediate. Sometimes an action might have consequences that don't show up until much later. Like in a game of chess, a move you make early on might not pay off until many turns later.
Can you break down some of the terms involved here? Like what's an agent, an environment, all that stuff?
Sure. The agent is the thing doing the learning, the decision maker. The environment is, well, the world the agent interacts with. It could be a virtual world, a physical space, a simulated stock market, whatever. Actions are the choices the agent can make. And the state is basically the current situation the agent finds itself in. Like in chess, the state would be the arrangement of pieces on the board. And the reward, well, that's the feedback the agent gets for taking a particular action in a particular state.
Okay, so unlike supervised learning, where you get that immediate right or wrong, the reward in RL might be delayed, and it's all about figuring out the long-term consequences of your actions.
Exactly. And that's a big challenge in designing effective RL systems. You have to figure out how to structure those rewards so that the agent learns the behavior you want without finding loopholes or unintended ways to game the system.
And how does the agent actually learn which actions to take? Like, is there some kind of internal map it builds?
You can think of it like that. There are two main things an RL agent tries to learn. One is a policy, which is basically a set of rules that tell it what action to take in a given state. It's like a strategy guide for the agent. The other is a value function, which estimates how good it is to be in a certain state. It's like the agent's prediction of how much reward it expects to get in the long run if it's in that state.
So the value function is all about looking ahead, figuring out the long-term payoff.
Exactly. It's not just about the immediate reward, but also about the rewards the agent expects to get down the line.
Fascinating. Are there different types of reinforcement learning algorithms, like different ways the agent can learn?
Oh yeah, there are a bunch. Some popular ones include Q-learning, deep Q networks, and policy gradient methods. They all have different ways of exploring the environment, updating their knowledge, and making decisions.
You mentioned deep Q networks. Does that involve deep learning somehow?
It does. Deep Q networks, or DQNs, they're like a hybrid of reinforcement learning and deep learning. They use deep neural networks to approximate those value functions we talked about.
Yeah.
And that's where things get really powerful, because deep learning allows those agents to handle much more complex inputs and learn much more sophisticated strategies.
Okay, we're going to circle back to that deep reinforcement learning stuff in a bit. But first, let's talk about the applications of plain reinforcement learning, the non-deep kind. Like, where is it being used right now?
Well, one of the most exciting areas is in game AI. You probably heard about DeepMind's AlphaGo, which beat a Go champion. That was a huge milestone for reinforcement learning. And then there are AI systems that have learned to play all sorts of classic video games, like those old Atari games, directly from the screen pixels. It's mind-blowing how they can learn to master these complex games with no human guidance, just through trial and error and those rewards. And, more recently you have OpenAI's Dota 2 bot and AlphaStar for StarCraft. These are all examples of reinforcement learning pushing the boundaries of what AI can do.
It's crazy to think that an AI can learn to play a game at that level, just by playing it over and over again. Like, what was the breakthrough that allowed for that? Was it just more computing power?
Computing power definitely played a role, but the real breakthrough was the development of new algorithms and techniques, like those deep Q networks I mentioned. They found a way to combine reinforcement learning with deep learning, and that opened up a whole new world of possibilities.
So games are a big one. What other areas are using reinforcement learning?
Robotics is another huge one. Robots can learn to walk, grasp objects, navigate complex environments, all through reinforcement learning. Imagine a robotic arm in a factory that learns to assemble a product through trial and error, getting rewards for speed and accuracy. That's already happening.
Wow. So it's not just about playing games, it's about real-world tasks, too.
Absolutely. And then there's autonomous vehicles. RL is being used to develop self-driving cars that can navigate traffic, make lane changes, all that stuff. And it's not just about cars either. We're talking about drones, robots, anything that needs to make decisions in a dynamic environment.
So it's about more than just reacting to what's happening right now. It's about planning ahead, making strategic decisions.
Exactly. And that's one of the key strengths of reinforcement learning. It can handle those complex, sequential decision-making problems where the consequences of your actions might not be immediately apparent.
Got it. Okay, so we've laid out the basics of supervised learning, deep learning, and reinforcement learning. Now, let's get into the comparisons, the head-to-heads. Starting with reinforcement learning versus supervised learning, what are the main things that set them apart?
The biggest difference is in the way they learn. In supervised learning, you have those labeled examples, those clear-cut right and wrong answers. The AI is told exactly what the correct output is for every input. But in reinforcement learning, it's more like learning from feedback, from those rewards and penalties. It's not told what the right answer is. It has to figure that out through trial and error.
So supervised learning is like having a teacher who tells you the answer, and reinforcement learning is more like learning by doing, seeing what works.
Exactly. And that difference in how they learn, it leads to a different objective too. Supervised learning is all about minimizing errors, making the AI's predictions as close to the true labels as possible. But reinforcement learning is about maximizing rewards. It's about figuring out the actions that will lead to the best outcome over time.
Makes sense. And what about the data they need?
Supervised learning needs that labeled data, those input-output pairs, where you know the correct answer for every input. Reinforcement learning, on the other hand, can often generate its own data through interactions with the environment. It doesn't need those pre-labeled examples.
So supervised learning is like studying from a textbook, and reinforcement learning is like learning by doing an experiment.
That's a good analogy. And that's one of the reasons why reinforcement learning is so exciting. It has the potential to learn things that we can't even teach it directly. It can explore and discover solutions that we might not even know exist.
That's really cool. So when would you choose one over the other? Like, when is supervised learning the better approach, and when is reinforcement learning the way to go?
Well, if you have a clear prediction task, like classifying images or predicting stock prices, and you have a lot of labeled data, then supervised learning is probably the way to go. But if you need an AI to learn how to act in a complex environment to achieve a specific goal, then reinforcement learning might be the better choice. Like, think about training a robot to navigate a maze. You could use supervised learning if you had a map of the maze and could label every possible path. But if the maze is unknown, or if it's constantly changing, then reinforcement learning would be a much better option.
Okay, that clarifies things. So supervised learning is great for prediction problems with lots of labeled data, and reinforcement learning is better for learning how to act in complex environments, especially when you don't know all the answers in advance.
Exactly. And I think a key takeaway here is that both approaches have their strengths and weaknesses. It's all about choosing the right tool for the job.
Right on. Okay, let's move on to the next comparison. Reinforcement learning versus deep learning. We touched on this a bit earlier, but I think it's worth digging a little deeper.
Absolutely. And again, it's important to remember that reinforcement learning is a learning paradigm, a framework for learning how to act. Deep learning, on the other hand, is a set of techniques, specifically those deep neural networks. So they're not directly comparable in the same way that, say, supervised learning and reinforcement learning are.
Right. So one is about the learning process, and the other is about the tool you use for learning.
Exactly. Reinforcement learning focuses on how an agent interacts with its environment, learns from feedback, and figures out the best actions to take. Deep learning, on the other hand, provides the model, those deep neural networks that can learn complex representations of data.
Okay, so how do their data requirements compare?
Deep learning, especially when it's used for supervised learning, needs lots and lots of labeled data. Like, think about training an image recognition model. You need millions of labeled images for it to learn effectively. Reinforcement learning, on the other hand, doesn't necessarily need that much pre-labeled data. It can often generate its own data through interactions with the environment. But that doesn't mean it's not data hungry. Complex RL problems can still require tons of data. It's just that the data is generated through experience, not pre-labeled by humans.
Got it. And what about the types of problems they're typically applied to?
Deep learning is really good at perception tasks. Things like image recognition, speech recognition, natural language processing. It's all about mapping complex inputs to specific outputs. Reinforcement learning, on the other hand, is better at decision-making tasks, like controlling a robot, playing a game, making strategic decisions in a complex environment.
So they have different strengths, but they can also work together, right?
Absolutely. And that's where deep reinforcement learning comes in. That's when you use deep neural networks as part of your reinforcement learning agent. Like those deep Q networks we talked about earlier, they use deep learning to approximate those value functions. And that combination has led to some of the most impressive achievements in AI, like those game-playing AIs that can beat human champions.
Okay, so deep reinforcement learning is like the ultimate power-up for reinforcement learning.
You could say that. It allows reinforcement learning to tackle problems that were previously impossible, problems with huge state spaces, complex inputs, continuous actions. It's a game changer, really.
And what about the output? Like, what do you get after you train a deep learning model versus a reinforcement learning agent?
With a deep learning model, you typically end up with a static function. You give it an input, and it gives you an output, like an image recognition model. You give it an image, it tells you what's in the image. But with a reinforcement learning agent, you get a policy, a strategy for acting in an environment. It's not just about mapping inputs to outputs. It's about making decisions, taking actions, and achieving goals.
So deep learning is about recognizing patterns, and reinforcement learning is about learning how to act.
That's a good way to put it.
Okay, I think we've got a pretty good handle on the differences between reinforcement learning and deep learning. Now let's zoom in on deep reinforcement learning specifically. What sets it apart from plain deep learning?
This comparison really highlights the difference between using deep learning for, let's say, static pattern recognition versus using it for dynamic, interactive decision making. Deep reinforcement learning, or DRL, emerges when you take those powerful deep neural networks and incorporate them into your reinforcement learning system.
So the deep in DRL refers to the use of deep neural networks.
Exactly. Those multi-layered networks, they become a core part of the agent's architecture. They might be used to approximate the value function, which tells the agent how good a particular state is, or the policy function, which tells it what action to take. And the reason this is so powerful is that it allows RL agents to handle those really complex, high-dimensional state spaces that traditional RL algorithms struggled with.
Like those Atari games where the AI was learning from the raw pixel data on the screen.
Exactly. That was a major breakthrough for DRL. The neural network, in that case a convolutional neural network, was able to learn directly from the visual input without needing humans to pre-process the data or tell it what features to look for.
So it's like the AI was learning to see the game world the way a human would.
In a way, yes. It was learning its own representation of the game world, its own way of understanding what was important and what wasn't. And that's one of the key advantages of DRL. It can handle those complex, unstructured inputs that traditional AI struggled with.
And how does DRL compare to just plain deep learning, deep learning without the reinforcement learning aspect?
Traditional deep learning is great for tasks like image classification, speech recognition, natural language processing. It's all about learning a mapping from inputs to outputs.
Yeah.
But it's not about interacting with an environment, making decisions, and learning from feedback. It's more passive, if you will.
So DRL is about learning to act, whereas traditional deep learning is about learning to recognize patterns.
That's a good way to put it.
Yeah.
And that difference is reflected in how you evaluate them, too. In DRL, you're looking at how well the agent performs in its environment, how much reward it gets, how well it achieves its goals. In traditional deep learning, you're looking at metrics like accuracy, precision, recall, those kinds of things.
Okay, can you give some specific examples of what DRL can do that traditional deep learning can't?
Sure. Think about those game-playing AIs we talked about earlier. AlphaGo, AlphaZero, those are all powered by DRL. They were able to learn to play those complex games at a superhuman level, something that traditional deep learning just couldn't do. And then there's robotics. DRL is being used to train robots to do all sorts of complex tasks, like grasping objects, navigating environments, even assembling products.
So DRL is pushing the boundaries of what's possible in AI.
Definitely. And we're just scratching the surface, really. As our computational capabilities continue to grow and our understanding of these techniques deepens, I think we're going to see DRL being applied to more and more complex problems that we can't even imagine right now.
It's pretty exciting stuff. So let's recap what we've learned. We talked about supervised learning, which learns from labeled examples. We talked about deep learning, which uses those powerful deep neural networks. And we talked about reinforcement learning, which learns by interacting with an environment and getting rewards or penalties.
And we saw how reinforcement learning and deep learning can be combined to create deep reinforcement learning, which is even more powerful and versatile.
And we saw how each of these approaches has its own strengths and weaknesses, and how they're being applied to a wide range of problems, from image recognition to game playing to robotics.
Exactly. And I think the key takeaway is that understanding these different approaches is crucial for anyone who wants to understand the current state of AI and its future potential.
Right on. So for our listeners out there, I encourage you to think about how these different AI approaches might be relevant to your own work, your own interests, your own lives.
And think about how the ability of AI to learn through interaction, like in reinforcement learning, might change the world in the years to come. I mean, what kinds of problems will we be able to solve? What kinds of new technologies will we be able to create? It's a really exciting time to be following AI.
Thanks for joining us on this deep dive. Until next time.